Hi guys, in the previous video we talked about differentiation and we saw that differentiation, when applying a set of rules of differentiation to a function, can help you find the gradient of the function. And today we're going to talk about the opposite of differentiation, which is integration, or sometimes we say anti-differentiation because it's really the opposite operation. So let's first talk about what indefinite integration is, right? Later on, we'll talk about definite integration, but first, we'll focus on indefinite integrals. Indefinite integrals are basically undoing the differentiation operation. So, for example, if I tell you that a function has derivative 2x plus 1, if I tell you the gradient of a function, right, can you figure out what the original function was? And in this case, right, for 2x plus 1, you can see that the function x squared plus x plus c, when you take the derivative, right, will give you 2x plus 1. Now, what is this c over here? This c over here, it can be any arbitrary constant because the derivative of a constant function, right, for example, derivative of 5 or derivative of 500 or derivative of 1000, right, as long as a constant is over here, taking the derivative of a constant will give you 0. So, this c over here, we can choose any c over here, and that will give us a valid antiderivative, a valid indefinite integral of 2x plus 1. So mathematically, we write integration as such. We write this long curly thing, followed by the function that we want to integrate, and dx. Right now, we write dx over here because we are integrating with respect to dx. For now, if I integrate a function, right, it's quite clear at the moment because we're only dealing with functions of one derivative, of one parameter, right? This dx kind of seems like it's useless because what else can we integrate with respect to, right? There's only x over here. But in future, when we talk about functions of multiple variables, when we talk about multivariate calculus, then in this case, when we integrate with respect to dx or dy, right, it would make a difference. So that's why we have to write this dx over here to tell the integral, or to tell ourselves that we're integrating with respect to the x variable. So yeah, so when we take the derivative, when we take the integral of a function, let's say f of x, and suppose it's capital F of x, right? This implies that derivative of the big F of x is the small f of x. Basically, whatever function I put in here, I'm asking the integral, right? When I integrate this function over here, I'm asking what is the function that when I take the derivatives gives me this thing inside. It's undoing the derivative. It's undoing the derivative. So yeah, so that's for indefinite integration. Now let's take a look at a few exercises before we move on to what definite integration is. So currently this is the algebraic way to approach to understand integration, right? We're doing algebra. Later on, when we talk about definite integration, I'll explain to you what's the geometric intuition for what the for what the integral calculates. So let's try the following exercises, right? Derivative of 5, integral of 5 dx is 5x plus c, where c is an arbitrary constant. So your math teachers will always tell you to write where c is an arbitrary constant, but in physics, most of the time, it's understood if you ignore it. Okay, so just like how I can take double derivatives, right? I can differentiate a function twice. I can also integrate a function twice. So in this case, integral of minus 10 dt is, let's perform the inner integral first, right? Is the inner integral be minus 10 t plus c. And then this thing, I'm integrating with respect to dt. So I integrate this thing again, and you'll see that this gives us, no integral sign here, this gives us minus 5t squared plus ct plus d. So now, because I integrated twice, right, there are two arbitrary constants that I can choose, because this is the general class of functions that when I differentiate twice will give me minus 10. In other words, if I differentiate this twice, right, if I differentiate this function, minus 5t squared plus ct plus d twice, right, you can see that c and d are arbitrary constants because if I differentiate it twice, right, d would disappear and ct would disappear because the first time I differentiated d over dt of ct, gives me c. And the second time I differentiate it, right, if I differentiate both sides again, then that will give me 0. So whatever c and d are, when we apply the second derivative to it, both of them would disappear and we'll be left with minus 10. This integral over here is very related to kinematics in, let's say, gravity, right? So that's why we're talking about this. Next, integral of sine 5t. This one's a bit more challenging, but it is important because this appears in things like oscillations and simple harmonic motion. We talk about the motion of a pendulum or motion of a spring mass system. So if we integrate this, we know that derivative of cosine 5t is minus 5 sine 5t, right? So if we kind of, we see that we kind of have this component over here that we want. So if I take both sides and I divide it by minus 5, then that implies that derivative of minus 1 over 5 cosine 5t is equals to sine 5t. And this is the function that we're integrating. So that implies that this is the integral. So this will be minus 1 over 5 cosine 5t plus c, where c is the arbitrary constant. And lastly, right, let's integrate 1 over x squared. This integral is important when we talk about gravitation. When we talk about gravitational potential, we're actually performing this kind of integral. So how do we integrate a fraction, right, a inverse of x squared, right? We can notice that if I take the derivative of x to the minus 1, right, this will give me minus 1 x to the minus 2, which is minus 1 over x squared. So this means that if I multiply both sides by minus 1, derivative of minus x to the minus 1 is equals to 1 over x squared. So you see that this is the thing on inside the integral. So this must be the antiderivative that we're looking for. So the answer is minus 1 over x plus c, where c is an arbitrary constant. You can see that when we perform anti-differentiation, right, when we take the antiderivative, or rather when we take the integral of something, both terms are used interchangeably. We kind of need to do a bit of guess and check work. We kind of need to use a bit of creativity to think of what function, when differentiated, will give me the thing that I'm trying to integrate. And it turns out that unlike differentiation, where there's a set of rules, for differentiation there's a set of rules where you can follow and systematically obtain the answer for any function that I give you. Integration in general is more challenging, and in fact, integration in general is not even well understood. And for example, right, there are functions like e to the minus x squared, where it's been proven that this is actually the error function, right, where we do not have an analytic expression for the antiderivative, for the integral of e to the minus x squared. And yeah, so in general, integration is hard, but there are a lot of techniques that we can use to find the integral of many classes of functions. But for most of physics, the integrals that we're performing will be doable. But when we move on to higher levels of physics, where we talk about research, then of course there are integrals that are more challenging to solve. So that's basically it for indefinite integration. In the next video, we'll talk about the geometric intuition for integration, what we are doing geometrically when we take the antiderivative.